Thank you all for coming. Welcome to lecture 5 of our course. I hope you're enjoying the course so far. Last lecture I wanted to do, but I couldn't because I had a flu and I couldn't really speak. This week it's much better. I think Tanush did a very good job doing the last lecture. This lecture today will be on computer vision. The lecture itself will be a bit more dry because we have a bit less quizzes, a bit less programming or live programming, but we need to go through some of the basic elements. And then afterwards we have the tutorial where you are able to put all these elements together and actually program yourself. We're almost done with the 4 key things that we see in convolutional neural networks. I want to go through the last one and then we do a break, I would suggest. And the last one is pooling. So what is pooling doing? Well, to some extent it might be that we have many different features. We have many different dimensions and we want to reduce that. We want to make it simpler. So we want to reduce dimensionality and that's where pooling comes in. And the idea is reduce dimensionality, but ideally we want to keep the key information. So we don't want to lose too much information. And one way to do this pooling is to apply an average filter. So we had that before. This average filter was reducing the dimensionality. So thereby, basically helping us to process the information later on easier. So average pooling we had already. This one is a 2x2 average filter. So if we apply it, basically, we apply it here, 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 and here. Why do we do it only for these 4 things here? Because we have a stride of 2, right? So we start here. The average of these values is 4.25. Then instead of moving the filter 1 step further, we move it 2 steps further because we have a stride of 2. So average of this one is 7. Then we apply it here, and these are these 2 values. So by applying average filter with a larger stride, we can reduce the dimensionality of our image significantly. So this is one very common pooling function we call. Another pooling function is a max pooling. Works very similar, but instead of taking average, we take the maximum value. So what we do is we look at these 4 values here again. We call them A, B, C, D because there's no easy way to write that as a filter. So what essentially happens is we take the maximum of them. Well, the maximum of these is 6. The maximum of these is 9. Maximum of these is 7, 8. Come on, Max. So thanks a lot. Max prepared most of the slides actually. I'm just doing a bit of PowerPoint karaoke. Maximum of those one is 8. So we'll correct the slides. And we have a nice example of that. So if you look at this P and ID again, relatively high dimension, what we can do is we can apply this max pooling function here with a kernel size of 2, stride of 2, and we reduce its dimensionality significantly. And if you look at it, well, it's still a P and ID, and I still can recognize most of the relevant unit operations. So to some extent, I can keep relevant information while reducing dimensionality here. So basically, these are the 4 core concepts that we find in modern machine learning architectures for computer vision. And I would suggest we do a break now till 10 minutes before, and then we continue with the real architectures for deep learning. Okay, shall we slowly continue? Okay. All right. So far we talked about filters, paddings, right, and pooling. And I know these have been very abstract concepts that are not easy to understand. Perfect, thank you. I know the concepts that I explained are not easy to understand. It's not clear how to put them together. I already got a few curious questions from students. If we do filters first or pooling first, or how do we put it together? And that's what I want to discuss now. But before, I want to do one step back to think about what are we actually doing, what is our goal. And I mentioned that in the beginning. In the simplest case, we talk about a classification problem. So basically, we have an image, and the goal is to predict what is the category of the image. And I guess you had that in the first assignment as well. If we talk about categories, usually we want to predict the probability for a certain category, right? So if we have an image here, we have our machine learning magic model. The output should be something like 70% car, 30% human, right? Or maybe 99% car, 0% human. So the goal more generally is to predict this vector here, where we have the image as an input, probabilities for all categories as an output. So if we have a bit more advanced model, we may have 40 categories or 500 or 1,000 categories. So we want to detect all different stuff. And I mentioned this is a supervised learning problem. So usually we have some kind of data, so training data, which are these images with a corresponding label. And by having this training data, what we can do is we can calculate an error, right? And that was a basic concept for machine learning that we learned already, also for standard classification problems and so on. So we have our image, we know, hey, that's a car. We have our machine learning model, we get the prediction of the machine learning model, and then we can calculate an error. Why do we do that? Because the error tells us, is it correct, is it wrong? We can differentiate that error. So we can find the derivative of the error with respect to the parameters of our model. And that tells us how can we, in which direction do we need to change the parameters in order to improve the model or the prediction. Okay? So that was a basic concept for backpropagation. So this gradient descent algorithm. And that's what we want to use here as well. And the general idea is that instead of having our filters predefined, like we did in the beginning, where I told you, hey, that's an average filter. This one is a filter where we have, zeros in one row and then -1 and 1 in the other one. What we have is we have more general filters. So the numbers in the filters are parameters of our model. So A, B, C, D, E, F, G, whatever. Right? And these are the numbers that we want to find now and we want to optimize during the model training. Okay, so on a very high level, that's our goal. We want to have training data, a lot of images with corresponding labels. We want to have our powerful computing model in between, where we have a lot of parameters, and these parameters are in the filters of our model. And then the model makes a prediction. We know better. We know the actual value because it's labeled data, because it's supervised learning, classification. Having the real true value, the ground truth, we can calculate an error. Using backpropagation, we can find the derivative of the error or partial derivative of the error with respect to the parameters. And that allows us to change the parameters, basically doing one step with the learning rate. You've seen that. Then our model might get a bit better, and then we'll repeat that procedure, right? So we're still talking about machine learning, we're still talking about backpropagation, we still talk about gradient descent. It's just that the model looks a bit different, and the input data looks a bit different. Because input data now, it's not just a vector, It's an image. It's a matrix, right? And to process that, well, we use filters, and the filters are not predefined. These are just these more general filters. Okay, so the general concept is a bit clearer. Any questions about that already? Yes.
What are the parameters in this model that we are optimizing?
Yeah, we come to that a bit later, but what you can think of at the moment is we want to apply this filter for this image here. And well, before each of these variables here had a specific value that we predefined. And now what happens is, well, these are just the parameters of the model. Like in a neural network, we have the weights and bias vectors, right? Here it's the values of the filters. Is that clear? Yeah, so what you do is, well, you initialize them randomly, essentially. Then you see how's the model doing. And then you change the parameters step by step in each epoch of the training. So the general concept is clear, yeah, because that's the most important one. Okay. And if we abstract that a bit, I'm not sure if we have an extra slide on that, probably later on, but I want to say that now anyways. So one of the key issues is, how can we come from this very high dimensional image to basically this small dimensional vector, you know, in the form of this one here, right? So you see that throughout the process, at some point we need to reduce dimensionality, right? Otherwise it's not going to work. But then on the other hand, we also need these features, these feature maps, in order to extract the relevant information from the image. The eyes, the ears, and so on. And then as a small repetition, basically these modern architectures for machine learning are called convolutional neural networks, or CNNs. Why are they called CNNs? Well, because they have convolutions, and convolutions, that was just another word for filters or kernels. So the stuff that we discussed before. And all the other elements that we discussed are also in there. In particular, the pooling, the sampling, the padding, all of that we can use in convolutional neural networks. And then there's one thing on top, which is this nonlinearity and activation function. And you've seen that in the standard neural networks already. So we don't only want to have this linear transformation, but neural networks also work because we have this firing of the ReLU activation or of other activation functions. So at some point we need to add